There is a moon of Jupiter where a person standing outside would spend an entire astronaut's career of permitted radiation in 24 seconds. Not 24 minutes. About the time it takes to find your keys. That moon is Io. The dose there is 3,600 rem a day, and it is also the most extraordinary landscape anybody has ever photographed. 400 active volcanoes, a lava lake larger than Lake Ontario, mountains twice the height of Everest. Now go 1.5 million kilometers further out, still around the same planet, and there is a moon where that same dose would take 6 years to reach, and where nothing at all has happened for 4 billion years. 4 moons, 1 planet. Line them up by distance from Jupiter, and you have also, without meaning to, lined them up by how long a person could stay alive on them. That is not a coincidence, and the thing doing the sorting is one of the 4. By the end of tonight, you will know exactly what it would take to live on Jupiter's moons, and exactly which of those 4 it would have to be. Get comfortable. If you enjoy finding out that the safest place in a solar system tends to be the emptiest one, a quick like and subscribe helps this channel reach more curious minds like you. Because by the end of this, the word live is going to mean something a little different than it did when you pressed play. Now, let's gently drift into this. You are lying still, and the room around you is doing nothing in particular. There is a ceiling above you that you could describe from memory. There is air moving through it slowly, at whatever temperature you have decided is comfortable, and it will keep moving whether you attend to it or not. Somewhere in the walls there is water under pressure, waiting. Under your back there is a floor, and under that floor there is more floor, and eventually there is rock, and the rock goes down for thousands of kilometers, and none of it is going anywhere tonight. You are, at this moment, doing something that almost nothing in the universe can do. You are surviving without effort. Nothing is being spent to keep you alive. No decision is being made. No system is being monitored. The oxygen arrives, the pressure holds, the temperature stays inside a band about 30 degrees wide, and above all of it, 400 kilometers of air and a magnetic field the size of a planet are quietly absorbing everything the sun throws at you, all night, every night, without anyone thanking them. Now hold that feeling, because we are going to take it apart. If you went outside tonight, and if the sky were clear, and if the season and the hour were kind, you would be able to find Jupiter without a map. It is not subtle. It is one of the brightest things up there, steady where the stars flicker, and it has been doing that for as long as anybody has been looking up. If you took a pair of ordinary binoculars outside with you and steadied your elbows on a fence post or a car roof, you would see something else. Beside Jupiter, in a rough line, there would be 3 or 4 faint points of light. They would look like stars. They are not stars. They are worlds, and they are the reason we are here tonight. In January of 1610, Galileo Galilei pointed a homemade instrument at Jupiter and saw the same thing you would see. 3 points of light in a line beside the planet, and then, on a later night, 4. He watched them for weeks. He noticed that they moved, that they changed places with one another, that sometimes one would vanish and reappear on the other side. And he came to the conclusion that they were not stars behind Jupiter, but objects going around it, which was, at the time, close to an unthinkable thing to say out loud, because it meant that not everything in the sky went around the Earth. He called them the Medicean stars, after the family that paid his wages, which is the sort of thing you did in 1610. The names did not stick. For most of the next 300 years, astronomers simply numbered them, Jupiter 1 through Jupiter 4, counting outward, and the names we use now came from a German astronomer called Simon Marius, who was looking at the same 4 objects at almost exactly the same time and lost the argument about who saw them first. Jupiter has other moons, incidentally. As of this August, the International Astronomical Union recognizes 115 of them, and that number has been climbing all year because most of them are captured rubble a few kilometers across on tilted, distant, backwards orbits. 4 of them are worlds. The rest are gravel with paperwork. Those 4 points of light are called Io, Europa, Ganymede, and Callisto. They are the Galilean moons. And they are not small. Ganymede is larger than the planet Mercury. Callisto is very nearly the size of Mercury. Io and Europa are each roughly the size of our own moon. Between them they hold, by every credible estimate, several times more liquid water than exists in every ocean on Earth combined. That is the fact that makes tonight's question a real question rather than a daydream. Because water is not one resource. Water is 4. It is something to drink. It is something to breathe once you split it. It is rocket fuel once you split it and chill it. And it is armor, which is the part almost nobody thinks about and the part that ends up deciding everything. So here is the question, and I want to put it plainly, because we are going to spend the next 2 hours refusing to answer it. What would it actually take to live on Jupiter's moons? Not to visit. Not to fly past with a camera. To be there, in a place with a name, and stay, and keep being alive the next morning. It has an answer. That is the part that surprises people. This is not one of those questions where the honest response is a shrug and a list of unknowns. There is a specific answer, involving a specific one of those 4 points of light, and it was written down by people at a space agency who did the arithmetic properly and put their names on it. By the end of tonight, you will know exactly what it would take, and exactly which of those 4 it would have to be. I will tell you now that it is not the one you would pick. It is not the famous one. It is not the one with the ocean everybody talks about, and it is very much not the one on the thumbnail. The answer is the least interesting object in the entire Jupiter system, and the reason it is the answer is precisely the reason it is uninteresting, which is a strange enough sentence that I want to earn it slowly rather than just say it. Because the interesting thing about these 4 worlds is not that they are different from each other. Of course they are different. The interesting thing is that they are sorted. Line them up in order of how far they sit from Jupiter, and you have also, without meaning to, lined them up in order of how long a human being could stand on them before dying. Those 2 orderings are the same ordering. That is not a coincidence, and it is not luck. There is a machine at Jupiter that does the sorting, and the fuel for that machine is one of the 4 moons, and by the end of tonight you will know its name and what it is doing and why it makes the other 3 what they are. For now, though, just hold the picture. 4 points of light beside a bright dot, close enough together that you can cover all of them with a thumbnail held at arm's length. One of them is on fire. One of them is an ocean with a lid on it. One of them is bigger than a planet and makes its own magnetic field. And one of them is a grey, cratered, entirely dead plain where nothing has happened for 4 billion years, and it is the only one of the 4 with an address. The question is which? And before we can even ask it properly, we have to be honest about what the question is actually asking, because the phrase, "live on a moon," is doing a lot of quiet work that nobody ever unpacks. So that is where we are going next. Not to Jupiter. Not yet. First, we are going to sit down and write out, item by item, what it actually means to live somewhere at all, what a place has to give you, and what you have to bring, and which of those things are negotiable. It is a shorter list than you would think. And when we apply it, one of those 4 points of light is going to fail on the very first line. There is a glass of water somewhere in your house right now, and it is sitting there at room temperature, uncovered, doing nothing. That glass is the whole problem in miniature. On Earth, it is so ordinary that it is invisible. Anywhere else in the solar system, that glass is a machine. It requires a pressure vessel to stop the water boiling away into vacuum, a heater to stop it freezing, a filter to keep it drinkable, and a supply chain that either arrived on a rocket or was manufactured on site out of ice. The glass of water is not a thing you have. It is a thing you maintain. So let us write out the list properly, because the phrase "live somewhere" hides at least 6 separate requirements, and people almost never separate them. The first is something to breathe. Not air specifically, oxygen at a partial pressure your lungs can work with, mixed into something inert so you do not set fire to everything you own. On Earth, this is free and infinite. Everywhere else it is a chemical plant that has to run continuously, forever, without a bad day. The second is something to drink and something to grow food in, both of which come back to water. Water is heavy. It is the single heaviest thing you would ever have to bring, which is why nobody sane plans to bring it. You plan to arrive somewhere that already has it. The third is warmth, and this is where intuition starts to fail. People imagine the problem in space is keeping heat in. Half of it is. The other half is getting rid of the heat you make, because a sealed habitat full of people, lights, pumps and electronics is a small furnace, and there is no air outside to carry the heat away. There is no wind. There is no cold breeze. The only way to lose heat in a vacuum is to radiate it, slowly, from large flat surfaces, and those surfaces have mass, and mass costs everything. So you are simultaneously fighting to stay warm, and fighting to dump heat, with the same fragile loop of fluid doing both jobs. The fourth is weight. Not weight in the sense of how much you can lift, weight in the sense of gravity pulling down on your skeleton, which turns out to be a signal your body reads constantly and adjusts to. Take it away, and the body starts dismantling itself, sensibly, from its own point of view. Bone that is not being loaded is bone that is not needed. We know what happens at 1 gravity, because we live here. We know what happens at approximately 0 gravity, because people have spent years in orbit, and we have measured them carefully. Bone in the weight-bearing parts of the skeleton is lost at something like 1 to 1.5% per month. Fluid that gravity normally keeps in your legs redistributes upward and stays there, which puffs the face, blocks the sinuses, and, this is the part that worries flight surgeons most, presses on the back of the eye. A large majority of astronauts on long missions develop measurable changes to the shape of the eyeball and the optic nerve head, and for some of them, the change does not fully reverse after they come home. What we do not know is anything in between. Not one data point. Nobody has ever lived at 1/5 of Earth's gravity, or 1/10, for any length of time. Every one of Jupiter's large moons sits somewhere between about 1/8 and 1/5 of a gravity. Whether that is enough to switch the body's maintenance systems back on, or whether it is close enough to nothing that the body treats it as nothing, is one of the largest open questions in human spaceflight, and there is no way to answer it from here. You cannot simulate gravity downward. You can only go. The 5th is time, in the sense of getting there and getting back, and being out of reach of every kind of help for the entire duration. On the Moon, help is 3 days away. From Mars, help is not available at all, and a conversation with home has a lag of somewhere between 4 and 24 minutes each way. At Jupiter, That lag runs from about 33 minutes to about 53 minutes each way, depending on where the two planets happen to be in their orbits. Ask a question. Wait an hour and a half for the answer. There is no version of that where anybody on Earth helps you with anything happening now. And the sixth, which is the one that sounds like a formality and is not, is this. The environment must not be actively killing you. Not slowly. Not in the way that everything eventually kills you. Actively. On a time scale you can measure with a watch. Now, for most of the last 60 years, the conversation about living somewhere else has been a conversation about two places, and both of them fail this list in the same tedious way. Our own moon has no water to speak of outside a few permanently shadowed polar craters, no atmosphere, a day that lasts a month, and dust that behaves like powdered glass. Mars has some water, an atmosphere at about 1% of Earth's pressure, which is functionally none, and a surface that is chemically hostile in ways we are still cataloguing. Both are hard. Both are also close, which is why they dominate the conversation. But notice what both of them are short of. Water. On the Moon, it is trace amounts in the coldest corners. On Mars, it is buried ice and ancient brine. Everything else about those places is an engineering problem, and the water is the constraint that shapes every plan. Now go out to Jupiter, and the constraint inverts completely. At Jupiter, water is not the limiting resource. Water is the ground. 3 of those 4 moons are believed to hold global liquid oceans beneath their surfaces, and the 4th, the one on fire, is dry only because it has been baked dry over 4.5 billion years. Europa's ocean alone probably contains 2 to 3 times all the liquid water on Earth, held inside a moon smaller than ours. Ganymede has an ocean. Callisto very likely has one. The surfaces of 2 of them are made of water ice you could, in principle, shovel. This is the first place in the solar system where the thing that has limited every plan we have ever made stops being the limit. And that is exactly why it matters that something else at Jupiter is very badly wrong. Before we get to what, though, I want to plant one assumption, because it is sitting inside the question we are asking and neither of us has examined it. When you hear the phrase, live on a moon of Jupiter, you picture a surface. You picture standing on something. A dome, maybe, or a base with windows, and outside the windows a landscape, and a person in a suit walking across it looking at things. That is the picture. It is the picture in every painting, every film, every mission patch. Hold on to that picture. Look at it properly. Because by the end of tonight, I am going to take it away from you, and the sentence that replaces it is the actual answer to the question in the title. For now, we have a list of 6 requirements and 4 candidate worlds. And before we can score any of them, we have to understand the thing that is going to do the scoring, because it is not any of the moons. It is not the sun. It is not distance or cold or gravity. It is a structure so large that if your eyes could see it, it would be one of the biggest objects in the night sky, bigger than the moon, bigger than anything, and it is completely invisible, and it is the reason 3 of those 4 points of light are closed to us forever. Somewhere in a clean room in California, before it was launched, a spacecraft called Juno was fitted with a box. The box is made of titanium. Its walls are about 1 centimeter thick, and it is roughly the size of a car boot. It weighs on the order of 200 kilograms, which on a spacecraft is an enormous amount of mass to spend on something that does no science at all. Inside it sit the flight computer and the most sensitive electronics. The box exists for one reason. Without it, Juno's brain would be destroyed within weeks of arriving at Jupiter. Europa Clipper, which left Earth in October of 2024, carries the same idea built out of titanium and aluminium alloy. Every serious spacecraft sent into the Jupiter system since the 1970s has carried some version of it, and the ones that did not carry enough of it came home damaged or did not come home at all in any functional sense. They are not shielding against the Sun. They are shielding against Jupiter. Jupiter is mostly hydrogen. Go far enough down inside it, and the pressure becomes so extreme that hydrogen stops behaving like a gas and starts behaving like a metal. The electrons come loose and move freely, and the material conducts electricity the way copper does. A very large fraction of Jupiter's interior is made of this stuff, and it is churning, and a churning conductor generates a magnetic field. The field it generates is about 20,000 times stronger than Earth's. Now add the second ingredient, which is spin. Jupiter is the largest planet in the solar system, and it has the shortest day. 9 hours and 55 minutes. Something 11 times the width of the Earth turns all the way around in less time than you spend at work. That rotation drags the entire magnetic field with it, and the field drags everything caught inside it, and the result is a structure that has no equivalent anywhere else in the solar system. It is called the magnetosphere, and its numbers do not sound real. It is about 20 million kilometers across on average. That is around 150 times wider than Jupiter itself, and roughly 15 times the diameter of the Sun. It stretches toward the Sun by 1 to 3 million kilometers, pushing back against the solar wind, and it streams away from the Sun in a tail that has been detected out past the orbit of Saturn, hundreds of millions of kilometers of it. It is the largest single structure in the solar system that is not the Sun's own bubble. Here is the household-scale version of that. If human eyes could see magnetic fields, and you went outside tonight and looked at Jupiter, it would not be a point of light. It would be a glowing shape several times wider than the full moon, hanging in the sky, slowly turning. It is up there right now. You simply cannot see it. And inside that structure, trapped, there are particles. A magnetic field of that strength does something specific to a charged particle. It does not let it go. An electron or an ion entering the field is bent into a tight spiral, follows the field line toward one magnetic pole, gets turned around, spirals back toward the other pole, and bounces between them, over and over, potentially for years. Meanwhile, Jupiter's rotation is flinging the whole field around every 10 hours, and every bounce and every turn is an opportunity for the particle to pick up a little more energy. Do that for long enough, and you get radiation belts. They are donut-shaped, centered on Jupiter's magnetic equator, and the particles inside them are moving at speeds that make them behave less like matter and more like a beam. Electrons in the inner belts reach energies of tens of millions of electron volts. When something like that hits a silicon chip, it does not warm it up. It knocks atoms out of the crystal lattice, one at a time, until the chip stops being a chip. We found out about all of this the way we find out about most things, which is by accident, and then by getting hurt. In 1955, two radio astronomers named Bernard Burke and Kenneth Franklin were using a ground-based array to survey the sky and kept picking up a strong, unexplained signal. It turned out to be Jupiter. At certain radio wavelengths, the planet is the second brightest object in the entire sky after the Sun, and what they were hearing was the sound of electrons spiraling in those belts. Nobody had expected a planet to be loud. Then, in December of 1973, Pioneer 10 flew through the system, and the radiation it absorbed was several times what the models had predicted. Instruments began sending back false readings. The spacecraft received commands nobody had transmitted, generated inside its own electronics by particles passing through them. It survived, barely, and the engineers used what it had learned to redesign Pioneer 11's encounter. 2 decades later, the Galileo orbiter, which stayed in the system from 1995 to 2003, absorbed roughly 4 times its design radiation dose over the course of the mission. It suffered repeated computer resets. Its tape recorder nearly failed several times and had to be nursed through faults by people on Earth, sending instructions across 40 minutes of empty space. It went slowly deaf, then slowly blind, and it kept working anyway. There is a further cruelty in the physics, which is that shielding is not simply a matter of putting more metal in the way. When a very fast electron is stopped abruptly in a dense material like lead, it emits a burst of X-rays on the way down. This is called Bremsstrahlung, braking radiation, and it means a thick, heavy shield can, in the wrong geometry, hand you a worse dose than a thin one. The materials that work best against Jupiter's electrons are light ones. Water, plastic, ice. Remember that. It is going to matter enormously in about an hour. Jupiter's magnetic axis is tilted about 10 degrees from its rotation axis, and it is offset from the planet's center, which means the belts are not neatly centered. They wobble. As Jupiter turns, the whole radiation environment rocks up and down, and anything orbiting inside it moves through varying intensities twice per rotation. It is not a static hazard. It has something like weather. All of that trapped material has to go somewhere eventually, and where it goes is Jupiter's poles. Earth has aurorae when the sun sends us a gust of charged particles, and they come and go over days. Jupiter's aurorae are permanent. They are hundreds of times more energetic than ours. They ring both magnetic poles continuously, and they have been burning without interruption for as long as anyone has had an instrument capable of seeing them. Jupiter is not occasionally lit at the poles. Jupiter is always lit at the poles, and the light is the sound of the machine running. Let me put you inside it for a moment. You are hanging in space above Jupiter's cloud tops, and you have been given the ability to see magnetic fields the way you see light. The planet below you is turning, visibly, fast enough that you can watch the cloud bands move. Around it, filling most of your view, is a shape that glows. It is not evenly bright. There is a broad, luminous band around the magnetic equator, brightest close in, fading outward, and it is rotating with the planet in a slow sweep that comes round again every 10 hours. It has structure, sheets, filaments, a flattened disk of current out at the middle distances where the field is being stretched by all the material it is carrying. It is quiet. Nothing about it makes a sound, and nothing about it moves quickly. It just turns, endlessly, like something very large breathing. And moving through it, in tidy circles, there are 4 small dark beads. The innermost one is buried in the brightest region, so deep in the glow that you can barely make it out against the light. The next one out is still well inside the bright band. The third is near the edge of it, where the glow has begun to thin. And the fourth one is far out, turning slowly through a region that is almost dark. You can see it clearly, because there is nothing much around it to hide it. 4 worlds, at 4 different depths, inside one enormous rotating structure. And from up here it is completely obvious that they are not in the same place at all. Come back to the room. That picture is the whole video. The 4 Galilean moons orbit inside the radiation belts at 4 different depths, and the amount of radiation reaching each of their surfaces is the single number that decides everything else. Every question about habitats, shielding, mass budgets, mission length and human survival collapses into it. Io orbits at about 422,000 kilometers from Jupiter. Callisto orbits at about 1,883,000. That is a difference of roughly 1.5 million kilometers, which sounds like a lot until you remember that Earth sits 150 million kilometers from the Sun. On a solar system map, you could not draw the gap between Io's orbit and Callisto's without a magnifying glass. Across that gap, the daily radiation dose at the surface drops by a factor of about 360,000. That is not a gradient. That is a cliff. And we are going to walk down it, starting from the top, starting from the worst place in the solar system that anybody has ever seriously photographed, which is also, and this is going to matter more than anything else tonight, the place that is making all of it happen. On the 8th of March 1979, a woman named Linda Morabito sat down at a screen to do a piece of routine work that nobody expects to be interesting. She was a navigation engineer on the Voyager 1 mission. Voyager had passed Jupiter days earlier and was on its way out, and part of her job was to work out precisely where the spacecraft was by photographing a moon against the background stars and measuring the offset. To see faint stars, you overexpose the image badly, which means the moon in the foreground becomes a blown-out white blob with detail lost. The moon was Io. And on the edge of the blown-out blob, off the limb, against black sky, there was a shape. A large, faint, crescent-shaped smear hanging above the surface where nothing should be. She checked it for artifacts. It was not an artifact. It was a plume of material rising roughly 300 kilometers above the surface of another world, and it was the first active volcano ever observed anywhere other than Earth. It was later named Pele. The extraordinary part is what had happened 6 days earlier. On the 2nd of March 1979, the journal Science had published a paper by 3 researchers, Stanton Peele, Patrick Casson, and Ray Reynolds, with the title Melting of Io by Tidal Dissipation. They had done the arithmetic on what Jupiter's gravity does to a moon on a slightly non-circular orbit, and they had concluded that Io should be internally molten and should show, in their words, widespread and recurrent volcanism. They published it 3 days before Voyager's closest approach, essentially getting the prediction out of the door before the answer arrived. Morabito has said she was not aware of the paper at the time. She simply found it. It is one of the cleanest sequences in the history of planetary science. A calculation on Friday, a photograph the following Thursday, and a completely new kind of world in between. Io is the innermost of the 4. It orbits Jupiter at about 422,000 kilometers, which is closer than our moon is to us, and it goes all the way round in 1 day and 18.5 hours. It is 3,642 kilometers across, a little larger than our moon, and the gravity at its surface is about 18% of Earth's, enough that if you dropped a coffee cup, you would have time to think about it on the way down. And it is the most volcanically active object in the solar system by a margin that is not close. Roughly 400 active volcanoes have been catalogued on Io. A recent thermal analysis identified 266 individually active hotspots. The heat flowing out of Io's interior averages somewhere between 2 and 3 watts for every square meter of its surface. Earth manages about 1/10 of a watt per square meter. Io is radiating something like 20 to 30 times more internal heat per unit of surface than the planet you are lying on, and it is doing it from a body 1/4 of Earth's diameter with no radioactive budget worth speaking of. The reason is the thing Peele, Casson, and Reynolds worked out. Io's orbit is not a circle. It is very slightly elliptical, and it stays that way because of Europa and Ganymede. Those 3 moons are locked into a pattern where Io goes round 4 times for every 2 orbits of Europa and every 1 orbit of Ganymede. It is called the Laplace resonance, and the effect of it is that the 3 moons line up in the same configuration over and over again and tug on each other at the same points in their orbits, repeatedly, in phase. Left alone, Io's orbit would have circularized billions of years ago. It cannot, because its neighbors will not let it. So Io's distance from Jupiter changes over the course of each orbit, and because tidal force depends steeply on distance, the bulge that Jupiter raises in Io's solid body rises and falls with it. Not in an ocean, in rock. The surface of Io moves up and down by something on the order of 100 meters, twice, every 1 day and 18 hours. That is a tide in solid rock, roughly the height of a 30-story building. All of that flexing generates friction, and all of that friction becomes heat, and the heat has nowhere to go except out through the crust, which it does violently and everywhere. The largest single feature is called Loci Patera. It is a lava lake about 180 kilometers across, larger than Lake Ontario, and it has been active every single time anybody has pointed an instrument at it since Voyager 1 arrived. Infrared mapping has shown a smooth temperature gradient sliding across its surface, from about 270 Kelvin at one end to about 330 at the other, which is what you would see if a wave of resurfacing were traveling slowly across a crust floating on liquid rock. Juno's close passes in late 2023 and early 2024, one of them at about 1,500 kilometers and one at about 30, returned the sharpest views since the 1990s and showed the lake floor as smooth and mirror-like. Away from the hotspots, though, Io is cold. 98% of the surface sits at around 130 Kelvin, which is about -143 degrees Celsius. The lava, where it erupts, exceeds 1,600 Kelvin, and in the hottest flows may reach 1,900. You could, in principle, stand on ground at the temperature of liquid nitrogen and watch, a few kilometers away, rock coming out of the ground hotter than anything erupting on Earth today. Io has no impact craters. Not one has ever been positively identified. Every other solid surface in the solar system is pockmarked, because everything gets hit eventually. Io gets hit too. But it buries the evidence. Volcanic material is being laid down across the whole surface at something on the order of a centimeter a year, which means that every square meter of Io is geologically younger than human agriculture. The moon repaints itself faster than the universe can mark it. There are mountains, and they are not volcanoes. Because so much material is constantly being deposited on top, the crust is being forced downward and sideways, and in places it buckles and tilts entire blocks upward. Beaux-Arts-le-Montes stands about 17 kilometers high, roughly twice the height of Everest above sea level, on a moon a quarter of Earth's width, with no atmosphere to soften the horizon behind it. The color of the place comes from sulfur, which is a peculiar element in that it takes on wildly different colors depending on how it has been heated and cooled. Geo is yellow and white, and orange and red and black in overlapping patches, and the pattern shifts on a timescale of months as new material is laid down. When the first Voyager images came back, a member of the imaging team looked at the screen and said it looked like a pizza, and the comparison has never been dislodged, partly because it is accurate and partly because there is no better one. What is happening underneath all of it is still argued about. A 2023 analysis published in Nature Astronomy looked at the distribution of heat coming out of 266 hotspots, including polar ones, and found the pattern consistent with either a global ocean of magma sitting beneath the crust or with heating concentrated in a shallow layer. Different lines of evidence, magnetic measurements from the Galileo orbiter, the heat flow map, the way Io responds to tidal stress, do not currently agree with each other. Whether the inside of Io is a shell of solid rock over a global liquid layer or something patchier is genuinely unresolved after 45 years of looking. There is even wind of a sort, which should be impossible. A study published in 2022 identified sediment being transported across Io's surface by flows generated where hot lava meets sulfur dioxide frost. The frost flashes to gas, the gas moves, and it carries fine particles with it. There are dunes on a world with almost no atmosphere, built by a wind that only exists for as long as the ground is on fire. There is an atmosphere, technically. It is almost entirely sulfur dioxide, vented from the volcanoes and sublimated from frost, and its pressure is around 1/1000th of Earth's, a vacuum by any human standard. But it does something no other atmosphere in the solar system does. For about 2 hours out of every Io day, the moon passes into Jupiter's shadow. The surface temperature drops from around -148 degrees Celsius to around -168. And at that temperature, sulfur dioxide gas cannot stay a gas. The atmosphere condenses and falls onto the ground as frost. It collapses. Then Io comes back out into sunlight, the frost sublimates, and the atmosphere reinflates. Io is the only body known to have an atmosphere that switches off and on, twice a week, forever. Water, on the other hand, Io does not have. It is the driest object in the solar system. Whatever it formed with was baked out and lost across 4.5 billion years of continuous heating. If you wanted to go there for the water, there is none. There is sulfur, silicate rock, metal, and heat. So on the checklist, Io fails the water line and fails the food line, and would fail the warmth line in an interesting way, because the surface is both far too cold and locally far too hot. But none of that is why Io is closed. Io is closed because of one number. The radiation dose at the surface of Io is about 3,600 rem per day. In the units used for human exposure, that is 36 sieverts every 24 hours. Here is what that means. NASA's career limit for an astronaut, the total dose a person is permitted to accumulate across an entire working life in space, set so that their lifetime risk of dying from a radiation-induced cancer stays under 3%, is 600 millisieverts, 0.6 of a sievert, for everything they ever do. On Io, an unshielded human being reaches that number in about 24 seconds. Not 24 minutes. Not a shift. The length of time it takes to find your keys. A single acute dose in the range of 4 to 6 sieverts kills roughly half of untreated people within weeks, and Io delivers that in under 4 minutes. I want to sit with that rather than move past it, because it is the specific sadness at the center of this whole subject. Io is, by a wide margin, the most spectacular landscape in the solar system. 400 volcanoes. A lava lake, larger than one of the Great Lakes, with a visible resurfacing wave crossing it. Mountains twice the height of Everest that are not mountains in any sense we have a word for. A surface younger than farming. Plumes standing 300 kilometers tall, silently, in a vacuum. An atmosphere that falls to the ground every few days and gets back up again. There is no view anywhere that we know of that compares to it. And a person standing in the middle of that, in a suit, would spend an entire career's worth of permitted radiation before they finished looking around. It is not that Io is dangerous in the way that a mountain is dangerous, where better equipment and more care improve your odds. There is no material anybody has proposed, and no suit anybody has drawn, that makes standing on the surface of Io survivable for a useful length of time. The mass you would need to carry would be the mass of a building. You would not be exploring. You would be inside a bunker that happened to be on Io, looking at a screen, and the screen could have been anywhere. So the thumbnail question has an answer, and the answer is no. Not now, not with better engineering, not in a century. Io is closed. Except that Io is not finished with this story. Not remotely. Because I have told you that Io sits in the worst part of Jupiter's radiation belts, and that is true, and it is also almost exactly backwards. Io is not sitting in the radiation belts. The radiation belts are coming out of Io. Picture a tap running. Not a dripping tap, a tap fully open, the kind that fills a bath in a few minutes. Now imagine that instead of water, what is coming out of it is a ton of material every second, and it has been running without interruption since before there were fish. That is Io. Roughly 1,000 kilograms per second of sulfur and oxygen, vented by the volcanoes, sublimated off the frost, knocked loose from the atmosphere by particles already in the neighborhood, leaves Io and does not come back. Some of it is heavy enough to fall back down. Most of it is not. Io's escape velocity is only about 2.5 kilometers per second, and the Moon is sitting in the middle of a rotating magnetic field that is very good at picking things up. What happens next is the part that reorganizes the whole picture. Those atoms get ionized. Once an atom has lost an electron, it is no longer neutral, and a magnetic field stops ignoring it. Jupiter's field grabs the ions and drags them along with the planet's rotation, and because Io orbits far more slowly than Jupiter spins, the field is constantly sweeping past the Moon, scooping up whatever it has just released. The result is a ring. A donut of ionized volcano exhaust, wrapped all the way around Jupiter along the path of Io's orbit, roughly 2,000 ions in every cubic centimeter, glowing in ultraviolet light. It is called the Io plasma torus, and it is one of the strangest objects in the solar system, a permanent structure made entirely of one small moon's breath. We noticed the torus before we understood the source. In 1976, 3 years before Voyager, ground-based astronomers detected sodium emission in a cloud around Io. Nobody knew Io was volcanic. Somebody had found the exhaust without knowing there was an engine. The material does not all stay in the ring either. Sodium and potassium from Io form an extended neutral cloud that reaches far beyond the torus itself and has been traced for hundreds of Jupiter radii, a faint, enormous haze of vaporized moon surrounding the entire planet, thin enough that you could fly a spacecraft through it without noticing, large enough that it dwarfs everything else in the system. And the ring does not sit still. Because Jupiter's magnetic axis is tilted about 10 degrees from its rotation axis, the torus is centered not on Jupiter's equator, but on its magnetic equator, which means the whole donut wobbles up and down as the planet turns. Io does not orbit through a fixed environment. It rises and falls through the densest part of the ring, twice on every lap, passing through material it produced itself on a previous lap, which is then knocked off it and put back into the ring and comes round again. It is the most closed loop in the solar system, and nothing about it has an off switch. Consider what that means about time. This has been running for 4.5 billion years. A tonne a second, for 4.5 billion years, is a number that stops being useful the moment you calculate it, so let me give it to you in a form that stays human instead. In the time it takes you to read this sentence, the mass of a small car has left Io permanently. In an hour, something like the mass of a fully loaded cargo ship. In a year, roughly 30 million tons. Io is not eroding in any way you would notice from outside. It is a very large object, and it is being resupplied from the inside by continuous melting. But it is nevertheless, slowly, permanently, being taken apart and redistributed into a glowing ring around another world. And it goes further, because Io is not only supplying material, Io is generating electricity. Move a conductor through a magnetic field and you induce a voltage. That is not exotic physics. It is how every power station on Earth works. Io is a large object. It has an ionized atmosphere wrapped around it, and Jupiter's magnetic field is sweeping past it at enormous speed. So Io behaves like a generator being spun by a planet. The potential difference across Io works out to more than 400,000 volts. The current that flows as a result, along the magnetic field lines that connect Io to Jupiter's north and south poles, is more than 3 million amperes. The power involved is on the order of a terawatt, which is comparable to the entire electrical generating capacity of the human species. That current path is called the Io flux tube, and it is not an abstraction. You can see where it lands. On Jupiter's poles, in ultraviolet light, there is a bright spot that marks the place where Io's field lines touch down, and as Jupiter turns, the spot is dragged across the polar region in a permanent glowing streak. Juno has photographed it repeatedly. Europa and Ganymede leave fainter footprints of their own, and Juno has now detected Callisto's as well, which was difficult because it falls close to the main auroral oval and is easily lost in the glare. So here is the reorganization. The radiation belts around Jupiter are not primarily fed by the Sun. Earth's are. Our belts are stocked with particles captured from the solar wind. Jupiter's are stocked from the inside, by a moon, at a tonne a second, and this is unique in the solar system. The material that makes Europa's surface lethal, that forces every spacecraft to carry a metal vault, that would kill an unshielded person on 3 of these 4 worlds, is Io's exhaust, ionized and accelerated by a magnetic field 20,000 times stronger than Earth's, powered ultimately by Jupiter's own rotation. Io is not a victim of the radiation environment. Io is the fuel. And there is something else sitting underneath that sentence, which I am going to leave alone for now, because it is the last thing I want to say tonight, rather than the next thing. But keep it somewhere. The resonance that will not let Io's orbit settle down is the same resonance that acts on the moon next door. Whatever it is doing to Io, it is doing a gentler version of it to Europa. Hold that. We will come back for it at the very end, and when we do, it is going to answer a larger question than the one in the title. It is the sort of thing that looks like a coincidence right up until the moment it stops looking like one, and then it never looks like a coincidence again. And I want to be careful here, because it is easy to hear that as a metaphor, and it is not one. It is a mass budget. Trace the particles that will one day break a chip on a spacecraft orbiting Europa, and they came out of a volcano on Io. The torus varies with Io's volcanic activity. Juno's radio measurements between 2016 and 2022 found the density of the ring changing in step with what Io was doing. A large eruption on Io alters the radiation environment for the entire Jupiter system within weeks. One moon, having a bad month, changes the survivability of a different moon 600,000 kilometers away. The energy for all of it comes from Jupiter's spin. The magnetosphere is a machine that converts a planet's rotation into accelerated particles, and Io is the load on that machine. Over geological time, this very slightly slows Jupiter down. Not by anything you could measure in a human lifetime, but the ledger balances. The planet is paying for this in angular momentum, and it has been paying for 4.5 billion years. So the ordering we noticed earlier, survivability rising with distance from Jupiter, now has a mechanism and a source. It is not that the moons happen to be arranged that way. It is that one of them is running a tap, and everything downstream of that tap is graded by how close it is to the mouth of it. Which brings us to the moon that sits directly downstream. The second one out. The famous one, the one that turns up in every list of places that might hold life, the one whose name you already knew before tonight. And it is going to be the hardest one to let go of. There is a photograph of Europa that most people have seen without knowing what they are looking at. A pale, cream-colored sphere, almost featureless, crisscrossed by thin reddish-brown lines that run for thousands of kilometers and cross each other at shallow angles, like a cracked eggshell that somebody has drawn on. It is one of the most recognizable objects in the solar system, and the first thing to understand about it is what is missing. There are almost no craters. Every other solid surface in the outer solar system is saturated with impacts. Callisto, which we will get to, is so heavily cratered that new impacts can only erase old ones. Ganymede is covered. Our own moon is covered. Europa has perhaps a couple of dozen features that can be confidently called impact craters on the entire globe, and the estimated age of the surface is somewhere between 40 and 90 million years. On planetary timescales, that is not old. That is this morning. Europa is also the smoothest solid object we know of. The highest relief anywhere on it is a few hundred meters. There are no mountains. There are ridges and cracks and jumbled zones. But if you shrank Europa to the size of a billiard ball, it would be smoother than the billiard ball. Something is resurfacing it, and the only thing that could be resurfacing it is what is underneath. Europa is the second Galilean moon out, orbiting at about 671,000 kilometers in 3.5 days. It is 3,122 kilometers across, slightly smaller than our moon, and the gravity at its surface is 13% of Earth's. Its surface is water ice, and its surface temperature runs from about 110 Kelvin at the equator down to around 50 at the poles. Beneath the ice there is an ocean, and the case for it is built from several completely independent lines of evidence, which is why it has moved from speculation to consensus. The most elegant piece of it came from the Galileo orbiter's magnetometer, and I love this measurement because of how indirect it is. Jupiter's tilted magnetic field sweeps past Europa as the planet rotates. A conducting shell inside Europa would respond to that changing field by generating its own opposing field. This is elementary electromagnetism, the same effect that makes an induction hob work. Ice does not conduct. Salt water does, very well. Galileo detected exactly that induced field, varying at exactly Jupiter's rotation period. Nobody saw the ocean. They detected the ocean objecting to being swept. The geology agrees. There are regions called chaos terrain where the surface looks as though it has been broken into rafts, rotated, tipped, and refrozen in place. You can trace the edges of blocks and see where they used to fit together, like ice on a pond in a thaw. The long dark lines, the lineae, show offsets consistent with a shell that has moved relative to what is under it. How thick that shell is has been argued over for 30 years, and in January of 2026 we got the best measurement yet. Juno's microwave radiometer, looking at Europa during a flyby back in September of 2022, returned an ice thickness of about 29 kilometers, plus or minus 10, in the region it could see. Call it 18 miles of ice. The same work found something less encouraging. The cracks and pores it could detect are only a few centimeters wide and extend only a few hundred meters down, which suggests they are not a useful route for material to travel from the surface into the ocean. Below that ice, the ocean is thought to be somewhere between 60 and 150 kilometers deep. And here is the detail that makes Europa the most talked about place in the solar system. That ocean sits directly on rock. There is no ice layer underneath it. Water is in contact with a silicate seafloor, and tidal heating is warming that seafloor from below. On Earth, that exact configuration, water touching hot rock, produces hydrothermal vents, and hydrothermal vents host entire ecosystems that have never seen sunlight and do not need it. They are also, on a growing number of people's lists, the most likely place life on Earth began. The volume of water down there is somewhere between 2 and 3 times all the liquid water on Earth. Every ocean, every sea, every lake and river and aquifer on this planet, 2 or 3 times over, inside a moon smaller than the one you can see out of the window. We have chemistry too, and we did not have to land to get it. Sodium chloride, ordinary table salt, has been identified in a region called Tara Regio from Hubble spectra, its signature produced by irradiation of the surface. In 2023, the James Webb Space Telescope identified carbon dioxide in the same region and, crucially, determined that the carbon came from inside Europa rather than from material falling onto it. Carbon in the ocean. Hydrogen peroxide, sulfuric acid hydrates and other irradiation products are spread across the surface. Oxygen is being manufactured continuously and for free. Jupiter's charged particles slam into the ice, split water molecules apart. The light hydrogen escapes to space, and the oxygen is left behind. In March of 2024, using measurements taken by Juno's particle instrument during a flyby that passed within 354 kilometers of the surface, a Princeton-led team published a production rate, about 12 kilograms of oxygen per second. 26 pounds, every second, made by radiation, for nothing. That number is important in a way that is easy to miss. It is much lower than people hoped. Earlier estimates had spanned from a few kilograms per second to over 1,000, and the measured value came in near the bottom of the range. Combined with the January 2026 finding that the cracks are shallow, the picture of oxygen from the surface reaching the ocean and feeding something down there got noticeably worse in the space of 2 years. There may also be plumes. Several times, Hubble ultraviolet observations in 2012, 2014 and 2016, astronomers have reported what looks like water vapor venting from Europa's south, and a reanalysis of old Galileo magnetometer and plasma data from a 1997 flyby appears to show the spacecraft flying directly through one without anybody realizing at the time. It is worth being honest about the status of this. Every one of those detections sits close to the limit of what the instrument could see. Repeated attempts to catch the plumes again have mostly come back empty, and the field is genuinely divided on whether they are intermittent or whether some of the detections are artifacts, or both. If they are real, they matter enormously, because a plume is a free sample of the ocean delivered to the surface, and you would not need to drill at all. The ice itself is probably not static. Warm ice is less dense than cold ice, so a shell tens of kilometers thick with heat coming in from below should convect, slowly, in great rising columns called diapirs, on a timescale of perhaps tens of thousands of years for a full overturn. The chaos terrain may be where one of those columns has pushed close enough to the surface to partly melt it from underneath. There is also evidence that the shell rotates slightly faster than the interior does, one extra turn relative to the core every few tens of thousands to hundreds of thousands of years, which would explain some of the offsets in the crack patterns. The lid may be very slowly turning on top of the ocean, like the loose lid of a jar. And Europa's surface is not clean. Sulfur from Io's plasma torus is being deposited on the trailing hemisphere, the side that faces into the flow of co-rotating material, staining it noticeably darker and redder than the leading side. Sit with that for a moment. Chemistry is being manufactured by volcanoes on one moon, carried 600,000 kilometers, and painted onto the face of another. The moons are not independent objects. They are components. That same bombardment sets a hard limit on how you would ever look for life there. The trapped electrons penetrate the top 10 to 20 centimeters of ice, galactic cosmic rays, which arrive from outside the solar system entirely and are far more energetic, reach a meter or more. Any organic molecule in that layer has been taken apart and rearranged, which means a lander cannot simply scoop the surface. It has to dig, or it has to find somewhere the surface is new. 2 spacecraft are on their way to answer some of this. Europa Clipper left Earth on the 14th of October 2024. It flew past Mars on the 1st of March 2025 at an altitude of 884 kilometers, using the planet's gravity to bend its path and taking the opportunity to test its ice-penetrating radar on the way through, which worked. It comes back past Earth in the first week of December this year. This December, a few months from now, passing at an altitude of around 3,000 kilometers, and then it heads out for the last time. It arrives in orbit around Jupiter in April of 2030. And then it does something that tells you everything about the environment. It does not orbit Europa. It orbits Jupiter on a long looping path and dips in to fly past Europa 49 separate times, taking data on each pass and then retreating back out to the safer part of the system to let its electronics rest. An orbiter at Europa would absorb a fatal dose of its own within months. The mission architecture is shaped, from end to end, by the need to keep running away. Let me put you on it before I tell you the last number. You are standing on Europa's ice. The sun is up, and it is a point, not a disk, 1/27th the brightness it has at home, small and hard and white, and the light it casts is roughly that of a heavily overcast afternoon. Above you, filling a fifth of the sky and not moving at all, is Jupiter. It does not rise, and it does not set, because Europa keeps one face turned toward it forever. The bands are visible. The whole thing turns slowly on itself, once every 10 hours, and you can watch it do that. The ice under your boots is not slippery. At 110 Kelvin, water ice has roughly the mechanical properties of rock. You could take a hammer to it and get chips, not slush. It stretches away flat in every direction to a close horizon, and running across it, disappearing over the edge of the world, are the lineae, dark, wide, hundreds of kilometers long, and from ground level completely unremarkable, just a slightly different shade of ground. There is no sound. There is no wind. Nothing on the surface is moving, and nothing has moved for as long as you have been standing there. And under your boots, 30 kilometers down, is more liquid water than exists on the entire Earth, warm at the bottom where it meets the rock, in the dark, doing whatever it has been doing for 4.5 billion years. Nothing about the scene tells you that. The only thing in the picture that is changing is the number on your dose meter. Because the radiation at Europa's surface is 5.4 sieverts per day. That is 5,400 millisieverts, against a career limit of 600. You would spend an entire permitted career of radiation exposure in under 3 minutes of standing there. A day on the surface is a dose that causes severe radiation sickness and death not long after in a person who is not treated. The people who study this describe it, in the flat language of the literature, as an amount that would cause severe illness or death in a human exposed for a single Earth day. So Europa has the water. It has the chemistry. It has the energy source. It has, by some distance, the best case for life anywhere in the solar system outside this planet. And it is a place where a person could not stand outside for the length of a phone call, which leaves exactly one option, and it is buried under 29 kilometers of the hardest material in the outer solar system. On the Kola Peninsula in the far northwest of Russia, there is a rusting metal cap bolted to the ground, about the width of a dinner plate. Underneath it is the deepest hole human beings have ever made. The Kola superdeep borehole reached 12,262 meters, a little over 12 kilometers, and it took 19 years. That project had every advantage it is possible to have. It was on Earth. It had an atmosphere to work in, so the crews could breathe. It had unlimited electrical power delivered by wire. It had unlimited mass. You could bring in another lorry load of drill string any Tuesday you liked. It had one gravity, so things stayed where you put them. It had a supply chain, a workshop, spare parts, and thousands of people. And it stopped in the end, not because the funding ran out, though it eventually did, but because at that depth the rock was hot enough, around 180 degrees Celsius, that it behaved like plastic, and the hole started closing itself behind the drill. 12 kilometers. 19 years. Everything going for it. Europa's ice shell is about 29 kilometers thick, and it is not the ice you are picturing. At around 110 Kelvin, water ice is not the material that goes into a drink. Its mechanical strength is comparable to rock. It does not yield, it fractures. It will blunt tools. It is, for engineering purposes, a mineral, and there are 29 kilometers of it between the surface and the most interesting body of water in the solar system. Every serious proposal for getting through it has the same basic shape, and it is a clever shape. You do not drill. You melt. The concept is called a cryobot, a long, narrow, nuclear-heated probe that sits on the surface, warms its nose, sinks into the ice under its own weight as the ice ahead of it turns to water, and lets the water refreeze behind it. It carries a communications tether that spools out as it descends, because no radio signal will pass through 30 kilometers of ice, so the tether is not a design choice, it is a requirement. At the bottom, in the ocean, it releases a small submersible. Prototypes exist and have been tested in terrestrial ice. Vehicles called Ice Mole and Valkyrie have melted their way through hundreds of meters of glacier, including at the Blood Falls system in Antarctica, and demonstrated that a melt probe can be steered rather than simply sinking. That is a genuine proof of principle. It is also about 1% of the required depth. The problems that remain are not small ones. A tether has to survive being frozen into a shifting shell for the entire descent and then keep working. The refreezing behind the probe is not neutral. It locks the vehicle in, permanently, so there is no reverse gear at any point after the first few meters. The ice is not pure water. Europa's shell contains salts and probably silicate inclusions, and those do not melt at the temperatures the probe can produce. They accumulate at the melt face as a growing layer of debris the vehicle has to get past. And underneath all of it sits the descent time, which for a realistic power budget is measured in years. And suppose you got through. Suppose the tether held and the salts did not stop you, and after some number of years the probe broke out into open water. The pressure at the base of Europa's ocean is estimated at somewhere around 130 to 180 megapascals. For comparison, the deepest point in Earth's oceans, the bottom of the Challenger Deep, sits at about 110. So a Europan submersible is not asking for exotic new materials. It is asking for something within striking distance of what has already been built and flown here by a handful of people, in vehicles the size of a small van. That is a rare thing in this subject, a requirement that is merely hard rather than impossible. There is also the question of what you would even be looking for. It is worth being careful here, because Europa gets discussed as though life there were a pending announcement rather than a hypothesis. What we have is a list of ingredients: liquid water in contact with rock, a heat source, carbon, sulfur, salt. That is a good list. It is not a finding. Nothing has been detected. The honest position is that Europa is the best place we know of to look, and looking is a thing nobody has done yet, and the two most recent measurements, the thicker-than-hoped ice and the lower-than-hoped oxygen supply, both moved the estimate in the unhelpful direction. Europa Clipper, incidentally, is not a life detection mission, and NASA has said so repeatedly. It is a habitability mission. It goes to find out whether the place could support life, which is a different and much more answerable question. Then there is a rule that sounds bureaucratic and is not. Planetary protection. If Europa's ocean might hold life, then putting a vehicle into it that carries terrestrial microbes is not a small mistake. It destroys the scientific value of the thing you went to study, permanently, and it does something ethically uncomfortable as well. Any vehicle that reaches that water has to be sterilized to a standard no spacecraft has yet achieved. This is the main reason Europa Clipper is a flyby mission and not a lander. It is also why the Galileo orbiter was destroyed. On the 21st of September 2003, having run out of propellant after 8 years in the system, Galileo was deliberately flown into Jupiter's atmosphere at high speed and burned up. It was not damaged. It was not obsolete. The mission team simply would not accept the small chance that a spacecraft assembled in a clean room on Earth in the early 1990s, not sterilized to modern standards, might one day drift into Europa. The decision was announced years in advance, and the reasoning was published in the open literature, and it is worth knowing because it is sometimes retold online as though Galileo were destroyed to hide something. What was being protected was the ocean. So Europa's ice is the barrier. 29 kilometers of rock-hard mineral over the best chance of finding life anywhere we can reach, and no method of getting through it that anyone has flown. Now turn it over. Remember what I said about shielding. Jupiter's radiation is dominated by very fast electrons, and when you stop a fast electron in something heavy like lead, it emits X-rays on the way down. Heavy shielding can hand you a worse dose than none. The materials that work are light ones, hydrogen-rich ones. Plastic. Water. Ice. Water ice is, as it happens, close to the ideal shielding material against the exact hazard that makes Europa lethal. Roughly 7 centimeters of it halves the dose. And because the reduction is exponential with depth rather than linear, doubling the thickness does not halve the dose again. It halves what is left, and then halves that. A meter of ice takes 5.4 sieverts a day and turns it into something small. 10 meters of ice takes it to essentially nothing. 10 meters. Out of 29,000. So the thing that stands between a human being and Europa's ocean is the same thing that would keep that human being alive once they were underneath it. The wall is the roof. You do not need to get to the ocean to survive on Europa. You need to get about as deep as a swimming pool is long, and then you can live there more or less indefinitely, as far as radiation is concerned, with the whole hostile sky sealed off overhead by frozen water you did not have to bring. There is a further advantage that follows from it, which is that you would not need to bring the shielding. This is the single largest cost in every crude deep space design anybody has ever drawn, the mass of the stuff you put between the crew and the sky, and the fuel required to move that mass across the solar system. If the shielding is already there, in place, in quantity, as the ground itself, the mass problem does not get smaller, it disappears. You arrive with a machine that makes a hole and a habitat that fits inside the hole, and the moon supplies the rest. And that is the moment the picture from earlier starts to come apart. The dome with windows. The person in a suit walking across a landscape. On Europa, that picture is not merely difficult, it is exactly backwards. The surface is the one place you cannot be, and the interior is the only place you can. The habitable volume of this moon is not its area. It is what is underneath. Which is a genuine answer to the question in the title, and it is not the answer, because there is a difference between surviving somewhere and living there. 10 meters of ice solves radiation. It does not solve power, it does not solve heat, it does not solve food, it does not solve getting there, and it does not solve the fact that every time you needed to go outside to fix something you would be spending your career. So Europa stays on the list, but only just, and only underground. And there is a quieter cost to that which is worth naming, because it is the sort of thing that only becomes real once people are actually living it. A settlement buried under 10 meters of ice has no view. Not a restricted view, none. There is no window that can be cut, because the window is the failure. Everything anyone there ever saw of the most beautiful object in the outer solar system would arrive on a screen, from a camera bolted to the surface, which somebody would occasionally have to go up and repair, and each of those repairs would cost a measurable slice of the rest of their life. 2 moons down. Both extraordinary. Both, for a person, effectively closed. And we still have not looked at the largest moon in the solar system, which is going to make a better case than either of them, and then, right at the end of making it, hand us a number that spoils it. Let us stop for a moment and put the pieces on the table, because we are halfway and there are now 3 separate things sliding past each other, and it is worth seeing them lined up before we go on. Imagine 3 rulers laid side by side, all of them running from Jupiter outward. The first ruler is radiation, and it falls as you move outward. At Io, 36 sieverts a day. At Europa, 5.4. Those are the 2 we have looked at, and the drop between them is already a factor of nearly 7 across 600,000 kilometers. Whatever comes next will be lower again. This ruler says, go outward, always, without exception. The second ruler is water, and it does not behave. Io, the innermost, has none at all. It is the driest object in the solar system. Europa has more liquid water than Earth. Whatever comes next, we shall see. But the pattern already tells you that water is not simply a function of distance. It is a function of how much heat a moon gets from being squeezed, and how much of what it started with survived that heating. This ruler is not a slope. It is a peak, and the peak is not at either end. The third ruler is how interesting the place is, in the sense of whether there is anything there worth crossing the solar system to see. And this one runs in the opposite direction to the first. Io, the deadliest, is the most extraordinary landscape we know of. Europa, the second deadliest, holds the best chance of finding life beyond Earth. The further out you go, the safer it gets, and the less there is. 3 rulers. One says, go out. One says, stop in the middle. One says, stay in. That is the whole difficulty of this subject in one sentence, and it is why the answer, when it comes, is going to feel like a compromise rather than a triumph. There is a 4th ruler, and it is the shortest one, so it is easy to forget it is there. Gravity. Io holds you at about 18% of Earth's pull, Europa 13%, and the two we have not met yet are 15 and about 12.5. Across all 4 moons that ruler barely moves. Every one of these worlds is somewhere between an 1/8 and a 1/5 of a gravity, which means that whatever a low-gravity lifetime does to a human skeleton, it does it to you on all 4 of them, and there is nowhere in the Jupiter system to escape it. That variable is not a choice you get to make. It is a condition of the whole address. And one more thing to hold before we go on, which is easy to lose sight of when the numbers get large. The gap we are walking down is small. Io orbits at 422,000 kilometers from Jupiter, and the outermost of the 4 sits at 1,883,000. That is a span of about 1.5 million kilometers. The Earth sits 150 million kilometers from the Sun. So everything we are talking about tonight, the difference between a place that kills you in seconds and a place that does not kill you at all, fits inside 1% of the distance from here to the Sun. If you drew the solar system on a sheet of paper, the entire drama would be inside the thickness of the pencil line around Jupiter. And notice something else, because it is the thing that will matter most at the end. Those 3 rulers are not independent. They are not 3 facts about the Jupiter system that happen to coexist. The radiation is high close in because Io is close in, and Io is the source. Io is the source because it is being squeezed. It is being squeezed because of the resonance, and the same resonance, gentler, squeezes Europa, which is why Europa has liquid water rather than a frozen ball. The water and the radiation are not separate phenomena that we have to trade off against each other. They are 2 readings taken from the same instrument at different distances. I said earlier that I would leave that alone until the end, and I am going to keep leaving it alone, because there is one more layer to it that we cannot see yet. What I will say is this. We have now closed 2 doors. We have 2 left. One of them is the largest moon in the solar system, and it is going to look for a while like the answer. And the other one almost nobody has heard of, and almost nothing has ever happened on it, and it is the one that NASA picked. The question in the title is still open. It has to stay open for a while longer, because the answer only means anything once you have felt the cost of every alternative, and we have not finished paying for the alternatives yet. Let us keep going outward. Take Mercury out of the solar system, set it down next to the 3rd of Jupiter's 4 moons, and Mercury is the smaller object. Ganymede is 5,268 kilometers across. Mercury is 4,880. Ganymede is the largest moon in the solar system, about 3/4 the width of Mars, and it is orbiting a planet as though it were a minor detail. If it were in its own orbit around the Sun rather than around Jupiter, nobody would hesitate to call it a planet, and it would be a more interesting one than Mercury. It orbits at 1,070,000 kilometers out, taking 7 days and 4 hours to go round. Its surface gravity is about 15% of Earth's. The temperature runs from around 70 Kelvin in permanently shadowed polar hollows up to about 152 Kelvin at the warmest point of the equatorial day, which is still around -120 degrees Celsius. And it does something no other moon anywhere does. It makes its own magnetic field. The Galileo orbiter found it in 1996, and the finding was genuinely unexpected. A magnetic field of that kind requires a liquid, conducting, moving core, the same arrangement that generates Earth's field. Nobody had assumed a moon would have one. Ganymede does, and it is strong enough to carve out a small magnetosphere of its own, with its own auroral ovals ringing its own magnetic poles. Stop and hold that geometry for a second, because it is the only example of it we know. Ganymede is inside Jupiter's magnetosphere, which is the largest structure in the solar system. And inside that structure, Ganymede maintains its own smaller bubble, a few Ganymede widths across, where its field wins and Jupiter's does not reach. Where the two fields meet, there are reconnection regions and permanent aurorae. It is a magnetic bubble inside a magnetic bubble, and there is nothing else like it anywhere. That field does what a field does. It deflects charged particles. And so, for the first time on this journey outward, the number improves dramatically. The radiation dose at Ganymede's surface is about 8 rem per day, 80 millisieverts. Europa was 5,400 millisieverts a day. Ganymede is 80. That is a factor of nearly 70 in one step, achieved by moving 400,000 kilometers further out and having a magnetic field of your own. But hold the celebration, because 80 millisieverts a day is not safe. It is merely no longer absurd. A NASA astronaut's entire career limit, 600 millisieverts, is spent in about 7.5 days of standing on Ganymede's surface. A month there without shielding is a serious radiation injury. A year is fatal. What has changed is the character of the problem. On Io and Europa, shielding is the entire mission, and on Ganymede, shielding is a solvable requirement. You would still live underground. You would simply not have to hide quite so far under. Ganymede has an ocean too, and the way we know is worth telling, because it is the second time on this journey that a moon has given itself away through its aurorae. In 2015, astronomers used Hubble to watch Ganymede's auroral ovals over several hours. As Jupiter's tilted magnetic field swept past, those ovals should have rocked back and forth by a predictable amount, about 6 degrees. They rocked by about 2. Something inside the moon was generating an opposing field and damping the motion, and the only plausible something is a layer of salty, conducting water. The ocean is estimated at around 100 kilometers thick, buried beneath a crust of ice roughly 150 kilometers deep. But there is a complication, and it is a significant one for anybody hoping this is a second Europa. At those pressures, water ice does not stay in the familiar form. It transitions into exotic high-pressure phases, denser than liquid water, which sink. Which means Ganymede's ocean is probably not sitting on rock at all. It is probably sandwiched, ice above, ice below, with the mineral chemistry that makes Europa's seafloor exciting, sealed off from the water entirely. Some modeling suggests the interior may be layered, with alternating liquid and ice phases stacked like a club sandwich, and in some of those models the lowest liquid layer does touch rock after all. It is unresolved. Ganymede also has an atmosphere, in the technical sense that there are some molecules above the ground. It is oxygen, made the same way Europa's is, by radiation splitting surface ice apart. It is so thin that calling it an atmosphere is a courtesy. The pressure is around 100 billionth of what is pressing on you right now. You could not breathe it, you could not fly in it, and it provides no shielding and no thermal buffering whatsoever. But it is oxygen, sitting on top of a moon covered in water ice, and it is a small reminder that the raw materials for keeping people alive are lying around the Jupiter system in quantity. The problem was never the ingredients. The surface tells a story that stopped. About 1/3 of it is dark, ancient and heavily cratered. The rest is lighter, younger terrain, cut by long parallel grooves and ridges, hundreds of kilometers long, formed by the crust being pulled apart. Ganymede was tectonically active once. It is not now. Its orbital eccentricity, forced by the resonance, is small today, so the tidal heating is modest, and the moon has been quiet for a very long time. That raises a puzzle nobody has fully answered. Callisto, which we are about to meet, is nearly the same size and nearly the same composition, formed in the same disk around the same planet at the same moment. And Callisto never sorted itself out. Its rock and ice are still mixed together. It has no core, no field, and no history of tectonics. Ganymede differentiated completely into iron core, rock mantle and ice shell, and Callisto did not. Two near twins, one of which had a violent early life and one of which did not. The best current explanation involves impact heating during formation. Ganymede, sitting closer in, would have been struck by objects arriving faster, having fallen further down Jupiter's gravity well, and the extra energy was enough to melt it. Callisto, further out, was hit more gently and stayed mixed. There is a spacecraft on its way to settle some of this. The European Space Agency's Jupiter Icy Moons Explorer, JUICE, launched on the 14th of April 2023. It carries 10 instruments, including an ice-penetrating radar, a laser altimeter, and a magnetometer built at Imperial College London, specifically to read the induced signatures of the oceans inside all 3 icy moons. It will not fly straight there. Chemical rockets cannot deliver that much energy, so it borrowed velocity from a double flyby of the Moon and Earth in August of 2024, the first maneuver of its kind ever attempted, then from Venus, then from Earth again. It arrives at Jupiter in 2031. It will make 21 flybys of Callisto and, deliberately, only 2 of Europa, because it was not built with a Juno-class vault and cannot afford the dose. And then, in late 2034, it will do something no spacecraft has ever done. It will enter orbit around Ganymede, around a moon that is not our own. In the entire history of spaceflight, no vehicle has ever orbited a moon of another planet. Everything we have sent to the outer solar system has either flown past or orbited the planet and made passes. Sit with the arithmetic of that for a moment, because it is very human. JUICE left the ground in April of 2023. It arrives in 2031 and settles into its final orbit in late 2034. That is 11.5 years between the launch and the thing the mission was built to do. The engineers who assembled that magnetometer, who tested it and calibrated it and signed it off, will be more than a decade older on the day it starts working properly. Some of them will have retired. Some will have moved to other projects and other countries. A few, statistically, will not be alive. They built an instrument, put it on a rocket, and accepted that they would watch it succeed from a completely different part of their own lives. That is what this kind of work actually is. Not the launch, which lasts an afternoon. The 11.5 years of waiting afterwards, holding a thing you cannot touch anymore. And it is not unusual. Galileo took 6 years to reach Jupiter. Juno took 5. Cassini took 7 to reach Saturn, and then worked there for 13. Everybody who does this signs up for it, knowing that the payoff arrives in a different decade of their life than the work did, and they do it anyway, and they do it again on the next one. And there is one more thing about Ganymede's field worth saying, because it cuts against the hopeful reading. Earth's magnetic field does not actually protect us from very much on its own. What protects you tonight is mostly the atmosphere, 5 tons of air above every square meter of ground, which is the equivalent of about 10 meters of water. The field helps by steering charged particles toward the poles, but the mass is what stops them. Ganymede has the field and none of the mass. So its magnetic shelter is real, and it is also the weaker half of the arrangement you are lying underneath right now, operating alone. So Ganymede is the best case so far. The largest moon in the solar system, a magnetic field of its own, an ocean, ice you could mine, and a dose rate that shielding can beat rather than merely resist. And still, a week outside spends a career. Still buried. Still a factor of 80 above what anybody would design for. Which leaves one. And before we go to it, we have to talk about everything that would still be trying to kill you, even if Jupiter's radiation belts vanished tomorrow, because that list is longer than the radiation list, and almost none of it is solved. There is a spacecraft in orbit around Jupiter right now, with 3 solar panels attached to it, and each one is about 9 meters long. Between them, they carry something like 18,700 individual solar cells. That is Juno, and it is the largest solar array ever sent into deep space, and the reason it had to be that large is a single number. Sunlight at Jupiter is about 1/27th of what falls on Earth. Here is what that means in practice. Those 3 enormous wings produce, at Jupiter, somewhere on the order of 500 watts. 500 watts is a household kettle at about 1/5 power. The same panels, if you brought them back and pointed them at the Sun from Earth's orbit, would produce around 14 kilowatts. Juno flies on a power budget smaller than the appliances in your kitchen, and it took an engineering effort of years to get even that. Now imagine 6 people living somewhere. Life support, lighting, heating, water processing, air scrubbing, communications, food production, and the machines that fix the other machines. That is tens of kilowatts, continuously, for years, with no downtime and no bad days. Solar cannot do it. Not with any array anybody could plausibly deliver. Radioisotope power cannot do it either, and this is worth knowing because it is the standard answer for the outer solar system. Radioisotope thermoelectric generators, the plutonium-fueled units that have powered the Voyagers and Cassini and New Horizons, produce a few hundred watts each and decline steadily as the fuel decays. And the fuel is the bottleneck. United States production of plutonium-238 stopped in the late 1980s. It restarted in 2013 at roughly 50 grams a year, with a stated ambition of reaching 1.5 kilograms annually. 50 grams a year is not a supply chain for a settlement. It is barely a supply chain for the occasional probe. Which leaves fission, a real reactor generating tens of kilowatts or more, running for a decade. Every serious crewed outer system architecture assumes one, and no crude-scale space fission reactor has ever been flown by anybody. It is not physics that stops it. It is money, politics, testing, and the fact that nobody has needed one yet. And then, having made all that power, you have to get rid of the heat. This is the part that catches people out. In a vacuum, there is no air to carry warmth away. The only way to lose heat is to radiate it as infrared light from a large flat surface, and radiators are heavy, and they have to face away from both the sun and the ground, and they have to keep working while the fluid inside them is being circulated by pumps that also make heat. On the International Space Station, the thermal control radiators occupy a substantial fraction of the entire structure, and that station is in sunlight most of the time and only supports a handful of people. A buried habitat at Jupiter, generating tens of kilowatts and surrounded by ice, has to move all of that heat through the ice without melting the structure it is buried in. Nobody has designed that. It is not obviously impossible. It is simply not a thing that has been done. Then there is food, which nobody in this conversation ever wants to talk about because it is the least glamorous item on the list and the one that has failed most reliably in every experiment. A crew consumes somewhere around 1.8 tons of consumables per person per year, if nothing is recycled. Recycle water and air, and you cut that enormously. But food is different, because food is not a substance you filter, it is a thing you have to grow, and growing it requires light, which requires power, which we have already established is the constraint. Every closed ecological system built on Earth so far has drifted. Chemistry has gone somewhere unexpected. A gas has appeared or disappeared. A crop has failed for reasons that took months to identify. Those experiments all had the enormous advantage of being on Earth, where you can open the door. A Jupiter habitat cannot open the door for 5 years. And there is the quiet one, which is spares. Every component on a spacecraft has a failure rate, and with enough components and enough years, something breaks. On the space station, when something breaks, a resupply vehicle brings a replacement within weeks. At Jupiter, the replacement either traveled with you 5 years ago, or it is manufactured on site out of local material, or it does not exist. Reliability compounds badly across long durations, and the usual engineering answer, carry 3 of everything, is another way of spelling mass, which is another way of spelling fuel. Let me slow down for a moment, because this is a lot of engineering and there is something worth just looking at. On Callisto, the outermost of the 4, one day lasts 16.689 Earth days, which means the sun comes up roughly twice a month, and it takes hours to do it. You are standing on a plane and the sky is black, because there is no air to scatter light into blue. Along one edge of the world there is a faint paleness. It builds slowly. There is no dawn chorus, no warming, no movement of air on your face. Over a long time the paleness resolves into a point, the sun, which from here is not a disk you could look at and see as a circle, but a very small, very hard, very bright dot, about 1/5 of the width it has from Earth. It clears the horizon over the course of an hour or more. And then there is light on the ground. It is not dark. It is about as bright as a heavily overcast afternoon at home, which is far more light than most people expect this far out. You can see clearly. The shadows are long, and they are absolutely black at the edges, because there is nothing in the air to soften them. And nothing warms up. The ground goes from about 130 Kelvin to about 160 and stops. That is the whole of the day's warming, 30 degrees, on a scale where water froze 130 degrees ago. The rock stays hard. The ice stays hard. Nothing melts, nothing runs, nothing steams. The sun rises, and the world does not respond to it in any way at all, and 8 days later, it sets again. And there is one more thing in the sky, and it never moves. All 4 of these moons are tidally locked, which means each of them keeps the same face turned toward Jupiter forever, the way our moon does toward us. So on the Jupiter-facing hemisphere of any of them, the planet simply hangs there. It does not rise. It does not set. It sits at the same point in the sky, permanently, going through its phases as the moon goes round, turning on itself once every 10 hours so you can watch the bands move if you have the patience. From Io, it would be about 19 degrees wide, which is roughly 38 times the width of the full moon as we see it, a band of cloud across 1/5 of the sky. From Callisto it is about 4.5 degrees, still around 9 times the width of our moon, and still the most prominent thing anywhere overhead. And on the far hemisphere of any of these worlds, you would never see Jupiter at all. Ever. 2 people could live on opposite sides of the same moon and disagree entirely about what the sky looks like. That is the ordinary daily experience of the place, and it will keep doing that whether or not anybody is there. Come back to the numbers. Cold is not solved by insulation alone, because you are also generating heat you have to dump. Gravity is not solved at all. At somewhere between 1/8 and 1/5 of Earth's pull, we simply do not know what happens to a human body over years, because nobody has ever tested any gravity level between 0 and 1. We know bone in weight-bearing parts of the skeleton is lost at around 1 to 1.5% per month in orbit. We know that a large majority of long-duration crew develop changes to the shape of the eye and the optic nerve, and that for some, the change does not fully reverse. Whether a fifth of a gravity switches those processes off, slows them, or does nothing at all, is unknown, and it is unknowable from here. Getting there takes years. Galileo took 6. Juno took 5. Zeus will take 8. Europa Clipper's route covers about 2.9 billion kilometers of travel to close a gap of roughly 600 million, because it cannot go directly and has to borrow energy from Mars and from Earth on the way. A crewed mission would want nuclear electric propulsion, which does not exist in flight-ready form, and even with it, the transit is measured in years each way. And once you are there, you are further from help than any human being has ever been, by a very large factor. A radio signal takes between about 33 and 53 minutes to travel each way, so the fastest possible question and answer with Earth is somewhere between an hour and an hour and 3/4. Nobody on this planet can help you with anything that is happening now. There is no rescue mission at any price, because a rescue would take 5 years to arrive. The longest anybody has ever stayed in space continuously is 437 days, set by Valery Polyakov aboard Mir between January of 1994 and March of 1995. The Mars 500 study sealed 6 volunteers in a mock spacecraft on the ground for 520 days. A round trip to Jupiter is roughly 3 to 4 times either figure in a worse radiation environment, with no possibility of opening the door. It is also worth noticing what has not happened. No human being has traveled beyond the immediate neighborhood of Earth since December of 1972. Every crude architecture for the outer solar system sits on top of a Mars program that has not been built, which sits on top of a lunar program that is not finished. The technical gap between here and a moon of Jupiter is real, and it is smaller than the gap between the plans and anybody's budget. So subtract Jupiter's radiation belts entirely, and the Jupiter system is still one of the hardest destinations anybody has ever considered. Power, heat, gravity, time, isolation. 5 problems, none of them solved, several of them not solvable without going first. Which brings us, at last, to the 4th point of light. The one nobody makes documentaries about. There is a surface in the solar system that is so completely covered in craters that no new crater can be added without destroying an old one. Every square kilometer of it is already occupied. Planetary scientists have a word for this condition. They call it saturation, and it means the surface has stopped recording history because it ran out of room. That surface is Callisto, and it is about 4 billion years old. Callisto is the outermost of the 4 Galilean moons, orbiting Jupiter at 1,883,000 kilometers and taking 16.689 days to go round. It is 4,821 kilometers across, which makes it the 3rd largest moon in the solar system and very nearly the size of Mercury, within about 1%. Its surface gravity is about 12.5% of Earth's, the lowest of the 4. Its average surface temperature is around 134 Kelvin, roughly minus 139 degrees Celsius. And nothing has happened there for 4 billion years. The largest feature is called Valhalla, and it is the biggest multi-ring impact structure known anywhere. At its center there is a bright plain about 600 kilometers across, and around that, concentric rings and troughs extend out to something like 3,800 kilometers in total diameter. That is around 16% of the moon's entire surface, taken up by the scar of a single collision. Callisto is dark. Its reflectivity is around 0.2, roughly 4 times darker than Europa, and the reason is a slow process rather than an event. Over billions of years, ice at the surface sublimated away into space, and it left behind everything that was mixed into it, carbon-rich material and silicate dust, as a lag layer, concentrated on top. The Moon has been slowly boiling off its own surface for the age of the solar system, and what remains on the outside is the residue. Underneath the dark layer, it is ice. That sublimation has done something else, which the Galileo orbiter's highest resolution images caught and nobody had predicted. It has sculpted the surface into fields of knobs and spires, tens of meters tall, standing everywhere across the plains. Nobody expected Callisto to have texture. It has a great deal of it, at small scale, and none at all at large scale. Here is what Callisto does not have. It does not have volcanism. It does not have tectonics. It does not have measurable seismic activity. It does not have a magnetic field of its own. It is not fully differentiated, its rock and ice never fully separated, so there is no clean core and mantle and crust, just a graded mixture that got denser toward the middle and then stopped. It is the largest object in the solar system that never sorted itself out. And the reason for all of that is one thing. Callisto is not in the resonance. Io, Europa and Ganymede are locked together in that 1 to 2 to 4 pattern, which keeps pumping eccentricity into their orbits, which keeps them being squeezed, which keeps them warm. Callisto is outside it. Its orbit is very nearly circular and has been left alone. It has not been squeezed for 4 billion years, and so it never melted, never differentiated, never resurfaced, and never became interesting. You can read that mixture straight off the scales. Callisto's density is about 1.83 grams per cubic centimeter, the lowest of the 4 moons. Io, which is essentially all rock and metal, is around 3.5. What that number is telling you is that roughly half of Callisto, by mass, is water ice, distributed through the whole body rather than concentrated in a shell. There is no shortage of water there. There is no drilling problem there either, because you do not need to reach an ocean 30 kilometers down when there is ice in the ground under your feet. It also has a trace atmosphere, carbon dioxide and molecular oxygen, at pressures far too low to matter mechanically, but present and detectable, and a further sign that the volatiles are still there rather than long gone. And we are about to learn a great deal more about it. JUICE, on its way now, will make 21 flybys of Callisto, more than of any moon except Ganymede itself, which will produce by far the best characterization of the place ever obtained. Ground-based work has already started. Thermal observations using the ALMA array, published across 2025 and 2026, have begun mapping the thermophysical properties of Callisto's near subsurface, which is a dry-sounding phrase for something quite practical. It means finding out what the top meter of the ground is actually made of and how it conducts heat. That is precisely the question you would ask if you were planning to put something on it. It probably still has an ocean, which is remarkable given all of the above. The evidence is the same induced magnetic signature that gave Europa away. Galileo's magnetometer picked up a conducting layer inside Callisto during several flybys, most plausibly salty water perhaps 100 to 200 kilometers down. There is a second, stranger line of evidence, and it comes from Valhalla. On worlds like our Moon and Mercury, a giant impact focuses seismic energy on the exact opposite side of the body and produces a zone of jumbled, chaotic ground at the antipode. Callisto's Valhalla antipode is undisturbed. Something inside absorbed the seismic waves before they could reconverge, and a liquid layer is the obvious candidate. It should be said clearly that Callisto's ocean is inferred rather than confirmed. The magnetic signature does not uniquely require water, and there is no obvious present-day heat source to keep it liquid, so most models call on ammonia acting as an antifreeze, which has not been detected. So, an ancient, dead, dark, cratered, unmelted, unsorted, geologically boring world with a possible ocean it does nothing with. There is nothing there. There is no eruption to photograph, no chaos terrain to puzzle over, no magnetic field to be surprised by, no plumes, no resurfacing, no story. And the radiation dose at the surface of Callisto is about 0.01 rem per day. 1/10 of 1 millisievert. Per day. Let me put that beside the others, because this is the moment the whole night turns. Io was 36,000 millisieverts a day. Europa was 5,400. Ganymede was 80. Callisto is 0.1. The charged particle flux there is roughly 300 times lower than at Europa, because Callisto orbits beyond the main radiation belts entirely. It is not deep in the machine. It is outside it. Remember the career limit, 600 millisieverts, the total a NASA astronaut is permitted across an entire working life. On Io, you spend it in 24 seconds. On Europa, in under 3 minutes. On Ganymede, in 7.5 days. On Callisto, standing outside, unshielded, in the open, you would take about 6 years to reach it. 6 years, on a surface, in the open, with a suit and nothing else. Put a few meters of Callisto's own dark regolith over a habitat, and the figure stops being a figure at all. It drops below what you are absorbing right now from the rocks under your house and the potassium in your own body. 6 years. That is not a hazard that dominates a mission architecture. That is comparable to what an astronaut accumulates simply from cruising through interplanetary space on the way anywhere. On Callisto, the radiation problem does not need solving. It needs monitoring. Let me take you down there. You are standing on a plain, and it is grey-brown and dark, and it is covered in craters at every scale you can see, enormous ones you can only recognize as a curve of the horizon, ordinary ones the size of a town, small ones the size of a room, and a fine peppering at your feet. Underfoot, the ground is dust over ice, and where a boot has scraped it, the ice shows pale. You are, though you cannot perceive it, standing inside Valhalla's ring system. The rings are hundreds of kilometers apart, so from the ground they do not register as a structure at all, just a low ridge in the distance, and then, much later, another one. The largest impact scar in the solar system is invisible from inside it. You would need to be in orbit to know it was there. Overhead, Jupiter hangs, about 4.5 degrees wide, 9 times the width of a full moon, motionless, banded, permanent. It will be in exactly that position tomorrow and in 10,000 years. The sun is up, small and hard and white. The light is that of a grey afternoon. Your shadow stretches out ahead of you with an edge like a knife. And here is what makes the scene land, which is a strange thing to say about somewhere this empty. Nothing here is trying to kill you quickly. There is no eruption. There is no chaos terrain shifting under the ice. There is no invisible flood of particles taking a slice out of your bone marrow while you stand and look at the view. It is cold, and it is airless, and those are engineering problems with engineering answers. Beyond that, the place is simply quiet. 4 billion years of quiet. The most boring world in the Jupiter system, and you could stand there and look at it for an afternoon and not have paid anything for the privilege. Go back to the 6-item list we made at the start and score it. something to breathe. There is water ice in the ground, and splitting water gives you oxygen, so yes, given power. Something to drink and to grow food in, the same ice in quantity, everywhere, no drilling required. Warmth, an engineering problem, solved by a reactor and by burying the habitat, which you would be doing anyway. Weight, 12.5% of a gravity, which is the one item Callisto fails as badly as everywhere else, and which nobody can score because nobody has the data. Time, 5 years, roughly, each way, which is brutal and is not disqualifying. And the last item, the environment must not be actively killing you. Callisto is the only place in the Jupiter system where the answer to that last one is simply no. The property that makes Callisto dull is the property that makes it survivable. It is outside the resonance, so it was never heated, so nothing ever happened there. And it is outside the resonance because it is far out, and it is far out because of the same orbital arrangement, and being far out is exactly what puts it beyond the belts. The boring and the safe are the same fact. You cannot have one without the other, and nobody gets to choose which half of it they take. And that is not a coincidence somebody noticed on the internet. It is the conclusion of a formal NASA design study that most people have never heard of, and it is where we go next. There is a document sitting in a public archive with a reference number on it. Anybody can read it. It has been sitting there since 2003, quietly, entirely correct, and almost nobody has ever looked at it. The title is Revolutionary Concepts for Human Outer Planet Exploration. The acronym is HOPE, which somebody at NASA clearly enjoyed. It was a conceptual design study run by the agency, and its stated objectives were to develop aerospace systems concepts that would allow human exploration missions into the outer solar system and to identify the critical technologies those systems would require. They needed a destination to design against. You cannot size a habitat or a propulsion system in the abstract. You have to pick somewhere and do the arithmetic. So they picked one of the 4 points of light. They picked Callisto. Here is what the study describes. A crew of 6. A launch around the year 2045 or later. Nuclear electric propulsion, because chemical rockets cannot deliver that much energy, and the transit time with anything less is unacceptable. A minimum stay of 30 days on the surface, and a total round trip of less than 5 years. And a surface base whose primary job is not science. Its job is production. You land on a moon that is roughly half water ice. You supply it with power. You electrolyze the ice into hydrogen and oxygen. You chill both into liquid, and you have manufactured conventional high-performance rocket propellant on-site, out of the ground, without having lifted a gram of it from Earth. That is the difference between an expedition and an outpost. An expedition brings everything it needs and leaves. An outpost makes what it needs and stays. The propulsion concept studied alongside it is worth a moment because it is a genuinely elegant idea. A companion paper looked at flying the mission with a magnetoplasma spacecraft, a variable specific impulse magnetoplasma rocket, usually shortened to its initials. The trick of it is that it can trade thrust against efficiency in flight. When you need to push hard, you run it one way and get more force out of less exhaust speed. When you are cruising and have all the time in the world, you run it the other way and get enormous efficiency from a trickle of thrust. It is the closest thing anybody has designed to a gearbox for a rocket. It has been in development for decades. It has never flown a mission. And the one-way transit under that kind of propulsion was estimated at somewhere in the range of 2 to 3 years. Which tells you where the 5-year round trip actually goes. Almost all of it is travel. The 30 days on the surface, The entire point of the exercise, the reason for going, is about 1.5% of the mission. Everything else is the commute. But the part of the reasoning that matters most, and the part that makes this whole night click into place, is why Callisto and not somewhere more interesting. It was chosen because it is outside the radiation belts. That was the deciding factor, exactly as we have been building toward. Everything else in the Jupiter system, however scientifically rich, is inside a machine that would kill the crew, and Callisto is not. And then the second reason, which is the clever one. From a base on Callisto, human operators could drive robotic vehicles at Europa and Ganymede in something close to real time. Think about what that changes. An operator on Earth trying to control a rover at Europa sends a command and waits somewhere between an hour and 1.75 hours for the answer. You cannot drive like that. You cannot react. Every action has to be scripted in advance, tested in simulation, uploaded as a block, and then you wait and hope. It is why planetary rovers move at the pace they do, not because the motors are slow, but because nobody can see what is happening until long after it has happened. From Callisto, the light time to Europa is a matter of seconds. Seconds. You could sit in a shielded room, buried under the surface of a dead grey moon, and reach across 1,000,000 kilometers and drive a vehicle across Europa's ice in something close to real time, watching it as it went. You could steer a melt probe. You could react to what it found. You could do, remotely, the exploration that no human being can ever do in person, and you could do it from the only address in the system where a human being can safely be. So the architecture is not a compromise exactly. It is a division of labor between a place that is safe and dull and places that are lethal and extraordinary, connected by the one thing that crosses the gap for free, which is light. And the logic generalizes beyond the Jupiter system, which is the third reason the study liked it. Callisto's gravity well is shallow, 12.5% of Earth's, so getting off it again costs very little. A base there could serve as a way station for anything heading further out, to Saturn, to Uranus, to wherever. The same reasoning that makes low Earth orbit useful as a place to stop and refuel applies to a moon you can leave almost for free, sitting on top of an ocean of fuel it is happy to give you. Callisto is not a destination in that reading. It is a service station on the only road out. Later work has come to broadly the same conclusion. A widely discussed concept study around 2015 revisited the idea of a crewed mission to Callisto in the 2040s and arrived at very similar answers about radiation, staging, and why the outermost moon is the one you go to. Nobody who has looked at this properly has picked a different moon. In a report at the end of 2003, NASA concluded that a crewed mission to Callisto may be possible in the 2040s. It is worth picturing what such a base would physically be, because the answer is unglamorous and completely determined by everything we have covered. It is not a dome. There are no windows. It is a set of pressurized modules sitting in a trench, with several meters of local material, the dark, dusty regolith that is lying there in unlimited quantity, pushed over the top of them by a machine. Callisto's radiation is low enough that you would probably not need to bury it for radiation at all. You would bury it for micrometeorites, for thermal stability, and because the material is free and moving, it is the cheapest work anybody there would ever do. Beside it, a reactor, set some distance away. Beside that, a plant that eats ice and produces oxygen, water, and rocket fuel. And somewhere inside, a room with screens in it, from which people drive machines on a moon they will never be allowed to visit. Now, I want to be very careful about how that lands, because it would be easy to make it sound like a plan, and it is not one. The study has never been funded. It has never been developed into a program. Nothing has been built. The technologies it assumes, a flight-rated nuclear electric propulsion system, a crude-scale space fission reactor, closed-loop life support that works for 5 years without opening the door, an in-situ propellant plant that runs unattended in cryogenic conditions, are individually unsolved, and every one of them would be a major program in its own right. The 2040s date is a design assumption, chosen so the engineers had something to size their systems against. It is not a schedule. Nobody is working toward it. It is also worth keeping the wider context in view. No crewed mission beyond the Earth-Moon system has ever been approved by any space agency anywhere. Every outer system architecture, Hope included, sits on top of a Mars program that has not been built, which sits on top of a lunar program that is not finished. The gap between here and Callisto is not primarily a gap in physics. What it is proof that the question in the title is answerable. Because there is a particular kind of quiet weight in that. In 2003, real people at a real agency sat down with the radiation maps and the orbital mechanics and the mass budgets and worked through the problem of putting 6 human beings on a moon of Jupiter. They did not conclude that it was impossible. They did not write a report explaining why it could not be done. They picked a moon, wrote down a crew size, specified a stay duration, costed the propulsion, described the fuel plant, and put a decade on it. And then it was filed. And the funding went to other things, as funding does, and the document has been sitting in an archive for more than 20 years, being right and being unread. That is not a tragedy. Nobody was wronged. It is just the ordinary shape of how this goes. The hard thinking is usually done long before anybody is ready to act on it, by people who understood perfectly well that they were writing for someone else's decade. The answer to the question in the title has existed, in writing, since before a lot of the people watching this were born. So let us finally say it out loud. All of it. What it would actually take. Somebody has a spade in their hands. That is the first image I want you to have, because it is not the one anybody expects at the end of a story about Jupiter. Not a rocket. Not a dome with a family looking out at the stars. A machine with a blade on the front, pushing grey dust over the top of a metal box, on a plane where nothing has happened for 4 billion years. That is what it would actually take. Let me say the whole of it plainly now, in 3 layers, because I promised you an answer, and it is time to hand it over. The first layer is the specification, and it is a short list. You would go to Callisto. Not Io, which is closed permanently. Not Europa, which holds the best chance of finding life beyond Earth and would spend your entire career's radiation allowance while you tied your bootlaces. Not Ganymede, which is the largest moon in the solar system, makes its own magnetic field, and still costs you a career in 7.5 days. Callisto, the 4th point of light, the dark one, the dull one, the one outside the belts. You would need nuclear electric propulsion, because the journey is 5 years and chemical rockets cannot make it shorter. You would need a fission reactor at the far end, because sunlight there is 1/27th of what falls on you tonight, and a settlement is not a spacecraft. You would need a closed loop for air and water and food that runs for years without anybody opening a door. You would need a plant that takes the ice out of the ground and turns it into oxygen to breathe and hydrogen to leave with. And you would need several meters of that ground on top of everything, which is why the picture I want you to keep is a machine with a blade on the front. 6 people. 30 days on the surface. Under 5 years, door to door. Written down in 2003 by people who did the arithmetic properly and then went home. That is the first layer. It is the boring one, and it is correct. The second layer is the one that takes something away from you, and I planted it hours ago so it would be waiting here. Right at the beginning, before we had gone anywhere, I asked you to hold a picture, the dome with windows, the person in a suit walking across a landscape, the base with a view. I asked you to look at it properly, because I was going to take it away. You do not live on a moon of Jupiter. You live in one. Every survivable version of this is underground. On Europa, 10 meters under the ice, with no window at all and everything you ever see of the sky arriving on a screen. On Ganymede, buried under whatever you can pile up. On Callisto, in a trench, under regolith, because the material is free and moving, it is the cheapest work anybody there will ever do. The habitable volume of the outer solar system is not surface area. It is interior. The surface is a place you visit, briefly, in a vehicle, on a schedule, with a number running in the corner of your visor. Every painting of this that you have ever seen has the geometry inverted. We keep drawing people standing on these worlds, looking out, because that is what living somewhere has meant for the whole of human history. It is the wrong picture. The right picture is a room with no windows, and a screen showing a place nobody in the room will ever stand. And the third layer is the one I have been putting off since the beginning, and it is the reason any of this is worth 2 hours of your night. Ask why. Not why Callisto. We have done that. Ask why the ranking exists at all. Why does survivability line up so neatly with distance from Jupiter? Why is the deadliest moon also the most spectacular, and the safest moon also the emptiest? That is a suspiciously tidy arrangement, and tidy arrangements in physics almost always mean you are looking at one thing and calling it two. Here is the chain, and it closes. Io, Europa, and Ganymede are locked in a resonance, 4 orbits, 2 orbits, 1 orbit, which will not let their paths settle into circles. Because the orbits stay slightly elliptical, the 3 moons are squeezed and released, over and over, forever. On Io, closest in, that squeezing is violent enough to keep the interior molten and drive 400 volcanoes. On Europa, further out, the same process, gentler, is what keeps an ocean liquid under 30 kilometers of ice at 110 Kelvin, 400 million miles from the sun, where every model says it should have frozen solid billions of years ago. So the resonance is the reason there is water to live off. And Io's volcanoes strip a ton of material into space every second, and Jupiter's magnetic field, 20,000 times Earth's, whipped round every 10 hours, ionizes it, catches it, accelerates it, and packs it into belts. So the resonance is also the reason there is radiation to hide from. They are the same fact. There is no version of the Jupiter system with the oceans and without the belts. The mechanism that put liquid water in the outer solar system, where it has no business being, is the mechanism that makes it unreachable. We have spent decades wanting one of those things and cursing the other without noticing that they come out of the same pipe. And that is not a peculiarity of Jupiter. Any giant planet with a strong field and resonant moons runs the same machine. Which means that wherever we eventually find water in the outer parts of other systems, and we will, because this arrangement is common, we should expect to find it behind the same wall. The universe appears to keep its liquid water in exactly the places that are hardest to approach, and it does so for a reason, and the reason is that the keeping and the hiding are one process. The moon is the fuel. I said that hours ago about the plasma torus, and it was true in the narrow sense. It is truer than that. Io is the fuel for all of it, for the belts, for the chemistry that stains Europa's face, for the permanent light on Jupiter's poles, for the entire reason this system is worth crossing the solar system to look at. Everything interesting about the Jupiter system, and everything lethal about it, comes out of one small world that is being needed by its neighbors and has been screaming into a magnetic field since before there was anything on Earth to notice. There is one more thing to say before we go, and it is the honest one, because I would rather leave you with an accurate feeling than a triumphant one. None of this is close. Not one of the enabling pieces exists in flight-ready form. Nobody has flown a fission reactor sized for a crew. Nobody has flown nuclear electric propulsion on a crewed vehicle. Nobody has run a closed life support loop for 5 years without opening it. Nobody has built a propellant plant that operates unattended at 130 Kelvin. Nobody has any physiological data at 1/5 of a gravity. And nobody, anywhere, has approved a crewed mission beyond the immediate neighborhood of Earth since December of 1972. But notice what is not on that list. Nothing on it is forbidden. There is no line in the physics that says, this cannot happen. Every single item is an engineering program that somebody has not started, and the reason nobody has started it is not that it is impossible. It is that it is expensive and slow and would be finished by people who are not the people who began it, which, as we saw with a magnetometer that will not do its job until late 2034, is a thing this field has been doing cheerfully for decades. So the honest answer to what it would take is not really a list of technologies at all. It is a statement about attention. The physics is settled. The destination is chosen. The document has been sitting in an archive since 2003. So go outside tomorrow night, if it is clear. Find Jupiter, which is easy, because it is the steady, bright one. Take a pair of binoculars and rest your elbows on something. And there they will be. 4 points of light in a rough line, indistinguishable from stars, exactly as they were for Galileo in 1610. Except now you know. One of them is on fire and is feeding a radiation belt at 1 ton a second. One of them is an ocean twice the size of every ocean on Earth, sealed under a lid nobody has worked out how to open. One of them is bigger than Mercury and makes its own magnetic field and has aurorae of its own. And one of them is a dark, cratered, saturated grey plain where absolutely nothing has happened since before this planet had continents, and it is the only one of the 4 with an address. They will look identical. They always do. 4 small points, close enough together that you could cover all of them with your thumbnail. And they will have moved. That is the part Galileo noticed, and it is still the best thing about doing this yourself rather than looking at a photograph. Come back 2 hours later and the arrangement will be different. Come back the following night and one of them may have gone behind the planet altogether. They are not a picture. They are a system, running, in real time, roughly 600 million kilometers away, and it has been running without pause for 4.5 billion years, and it does not require anybody to be watching. Tonight, while you sleep, Io will pass through Jupiter's shadow, and its atmosphere will fall to the ground as frost, and then it will come back out, and the frost will rise again. That will happen twice before the weekend. It has happened without a single missed cycle, something like 1 trillion times. That is what it would actually take to live on Jupiter's moons. A reactor, a spade, 5 years, and the willingness to give up the window. And it would have to be the dull one. It was always going to be the dull one.